Hello everyone. Today we're going to talk about equilibrium of a particle. What we consider a particle, let me give you some examples here. We are going to analyze problems like this right here. In this problem, this ring at A can be considered as a particle to analyze the equilibrium of this system. If point A is in equilibrium, the whole system is in equilibrium. So point A will be subject to a force here from the chain AC, another force here from the other chain AB, and another force here from the other chain going down. That is basically holding the weight of the engine. So this is what we are going to be treating as a particle for the purpose of our analysis here. Let me show you some more examples. This is another example that we can consider some portions of this as particles in order to analyze the equilibrium of the whole system. For example, this point B here, it will be considered as a particle, and it will have a force of a cable here, and another force of a cable here going up at 15 degrees, and then the weight of the traffic light here. So those will be the forces acting on the point B, and B will be the particle that will be analyzing in order to get to the solution to this problem. Same thing will happen with C. C will be another particle with some force on this direction, another force in this direction, and another wave going down here. So that's the way we're going to treat this as particles. One last example. This is another typical example that we can find here. The particle to be analyzed here will be point A, and point A will be subject to a force from the spring going here, force of the spring, then some force here going down, the hand pulling down, and another force here to the cable, to the rope that is acting on that. So this point A will be our particle to be analyzed. So let's take a look at some elements that we will find here. For example, the springs. We will be dealing with the springs. Let's talk a little bit about the springs. We have to be able to deal with the springs, know exactly how they work. So we have to give it a little treatment to the equation of the springs, basically Hooke's law for the springs. You probably remember from your physics that when you have a spring and apply force, this apply a force that is pulling on the spring has an initial length, let's call it L sub 0, when there is no force here. As soon as we apply force on the spring will stretch and will increase its length. Let's say that this length is x, and now we are applying a force here. Let's call it F sub P. This F sub P is opposite to the force that the spring applies here, or the spring reacts with the spring force as soon as we apply the force P. This force P is proportional to the elongation that we produce on the spring. And the force that the spring makes in reaction is exactly the same force, but it's in the opposite direction of the elongation. So we have this other formula. It's basically the same formula, but this one is more known as the Hooke's law for springs. So we need to be aware of this equation. Force equal Kx is the general equation for springs. Force equal Kx, where K is the spring constant. And it's basically telling us how much force you need in order to produce a given amount of, or a unit amount of elongation. Let's make an example here. Let's say a force is applied to a spring of 800 newtons, and the spring has a constant of, let's say, 500 newtons per meter. So what is the elongation on the spring? So we have the equation F equal Kx. So from here we can get that X will be equals to F over K. So it will be here 800 newtons over 500 newtons per meter. So this will give us 8 over 5. .6 meters. So you have to be very familiar with this expression. We will be using it eventually in some of the problems, and you have to be able to find either the elongation given the force, or the force given the elongation, or the spring constant given the force and the elongation. Let's see, what else? We will be using also pulleys. You will find pulleys during the course. In many instances, we use pulleys in real life. A little word about pulleys. Everybody knows a pulley. No matter what happens on the pulleys, what is the angle of the force, no matter what is this angle or what is the other angle here, the force, let's call it tension 1, tension 2. It doesn't matter what angles or what is the situation, tension 1 is equal to tension 2. The force applied by one, the cable that goes to one side of the pulley is equal to the force on the cable that goes on the other side. This is true in every pulley. This is the pulley right here. And across a pulley, there is always a cable. And the tension on one side of the cable will be the same as the tension on the other side of the cable. Another consideration, ropes. Ropes. Actually, ropes, chains, cables, or the like. This can only apply tension. Tension. They can only pull. They cannot push. You can pull with a cable. You can pull with a chain. You can pull with a rope, but you cannot push. You cannot push. If you try to push with a cable, the cable just becomes all loose. But you can never push with one of these, a chain or a rope. That will give you a clue about the direction of the force that the element is applying. And one last thing that we want to consider here is the frictionless surfaces, like this one right here. Just one word about this. Just one word about this. If you have a surface that is thought to be frictionless or a smooth surface, you have to know that the force that the surface applied on the subject in analysis is normal to the surface. So here, if we make a free body diagram of this wheel here, we will have a force here that is perpendicular to the surface. So this angle is 90 degrees. and then we have another force we call T. So the force on a smooth surface is normal, is perpendicular. It's perpendicular because when there is no friction here, if there is no friction here, this is a force of friction, no friction, so this force doesn't have this component, because if there was component, this force will not be perpendicular, but we will have this kind of component here, which this will be the frictional force, and this will be the normal force. Then you will have an angle here. But for a smooth surface, this force doesn't exist, so the only possibility is that this force is perpendicular to the surface, so 90 degrees. Remember, every time you have frictionless surfaces or smooth surfaces, the contact force between the two, or the force of the object, will be perpendicular to the surface. Don't forget that. Okay, so now we can come to study the equilibrium of particles. If we talk about the equilibrium of a particle, we are talking about a particle that is not moving or is moving at a constant speed. That's what is considered equilibrium. So we are talking about the Newton's second law, force equal mass times acceleration, in a particular case when the acceleration is zero. When acceleration is zero, we have equilibrium. So in order to get, if we get acceleration equal to zero, Newton's second law becomes equals to mass times zero. So force equal mass, force equals to zero. In a more general sense, Newton's second law refers to not just a force, but the resultant force of all the forces applying on a specific object has to be equal to zero. The more general equation should look something like this. If you have, we are talking about particles, if you have several forces acting on a particle here, and you get the summation of all these forces, F1, F2, F3, F4, then if you do the summation of all those forces, has to be equal to zero in order to have a guaranteed equilibrium, the equilibrium of the particle. In order to analyze, or in order to find the resultant of the forces, we already studied how to calculate it using the rectangular components, kind of like a more organized way to do it. The way we do that is we get all the components in the x direction and all the components in the y direction, and we get the summation of in each direction, and that's how we calculate the result. And basically we do is we calculate the summation of all the components in the x direction, and we calculate all the components in the y direction by summation of all of them. And that's how we calculate the resultant. The resultant, the magnitude of the resultant would be all the summation in the x direction square, and all the summation of the y direction square. And if we want this resultant, this zero, then this has to be zero, and this has to be zero. So from then we have that the summation of forces in the x direction has to be zero. The summation of forces in the y direction has to be zero. This is required. This is required and is sufficient in order to guarantee the equilibrium of a particle. The summation of forces in the x direction equal to zero guarantees that the force doesn't have any acceleration in the x direction, and the summation of also for the summation of forces in the y direction being equal to zero guarantees that there is no acceleration in the y direction. So the particle is in equilibrium in the plane, in 2D plane. These two equations is what we will going to call equilibrium equations. Equilibrium equations. And they will be our tool to study the equilibrium of a particle. Basically, what we'll have to do is to find some forces or some other or geometry, depending on the problem. So we count on these two equations in order to solve whatever unknowns we have. That's all we have. That's it. Basically, we need to decompose all the forces in the x components and the y components, apply these two equations, and based on that, calculate or find unknowns that we might have in any specific example or problem. Okay, well, so we just have to do some examples. Okay, let's take a look at this example. I encourage you to keep watching these examples because in the previous discussion, or even in these examples, we cannot do all the examples possible here. I'm gonna tell you a few hints, a few tips that will help you to solve these problems, but there are all sort of problems here. It's impossible for me to do an example that considers all possibilities. However, I will tell you some tips that will help you with the solution of all the problems. Okay, let's take a look at this one. Two cables are tied together at C and are loaded as shown. Determine the tension in cable AC and in cable BC. First, you should do what is called a free body diagram. That for a particle, a free body diagram is just a point. It's just a particle. Particles is just a point. So basically, you have to draw a point, and then you replace all the elements that touch that point by the forces that those elements exert on the point. In this case, we have the force of 500 newtons going to the right, 500 newtons. And the forces of the other elements that touch the point. Here there is an element that touch the point below is the bar BC. So you replace the bar BC by a force. And you remove the bar and you put the force. And then you have the other force, the AC. So you put the force instead of the bar. You should put the name and the direction of the forces that you know. You have to put them very clearly, the name and the direction of the force. If they are known, you have to put it the way they go. And if the force is unknown, you will put a name that has some logic. In this case, we could put, let's say, this one force BC, and this one force AC. Some name that has some logic, some reference to the actual example, the actual problem. And then the direction is not really important. If you know the direction, because for example, you know that you're talking about a cable, and you know the cable only can pull, cannot push, so you know the direction. But if you know the direction, well, put it in the direction that you think is correct. But if you don't know the actual direction of a force, it doesn't matter. You just put any direction you want. And at the end, when you find the solution, you will find that if your solution is positive, it means that the direction that you assume was correct. And if the solution gives you a negative number, it means that the direction that you assume was actually incorrect, and it has to go in the opposite direction. We're talking more like sense. Instead of, if you assume it is going this way and you get a negative, then it's actually going that way, in the opposite direction that you assume. Okay, Another thing that you have to do is you have to draw some axes, X and Y axis. In this case, we will put X axis in this direction and Y axis in this direction. Usually it's okay to put X and Y direction like horizontal and vertical, but in some other cases could be convenient to put the axis with a little rotation. I will show you in another example why is that. Let's continue in this simple example. Let's keep it simple in the first one. And you have to put into your free body diagram also other geometrical conditions that you might have. In this case, we have a 30-degree angle, 30-degree angle here. And then 50-degree angle here. This is 50. So this angle here is 50 degree. Okay. So this angle is 40 degree. And this angle is 60 degree. And then all the elements in the drawing, in the free body diagram, then we proceed to write the equations of equilibrium. The equation of the equilibrium go summation of forces in the x direction has to be equal to 0. So let's put all the components. Let's make the composition here. So we have here the components f ax, acx, and then he will have the component f acy, and then we will have here the component the f bcx. This one will be the component f dcy. We have some auxiliary here. So let's establish the first equation, summation of forces in the x direction. We have 500 newtons going in the positive direction of the x-axis. So the other to go in the negative direction according to the sense that we assume here. So this will be minus FACX, which is FAC cosine 40 degrees. And the component FBCX is also going to the left, so it's also negative FBC cosine of 60 degrees. And if there is no more forces, then this is equal to 0. Now we set up the equation of forces in the y direction equals to 0. And then we have only two forces, this one and this one. So FACY is FAC sine of 40 degrees, and FBCY is negative, it's going down. So it's FBC cosine of 30 degrees or sine of 60 degrees, whichever is the same. Sine of 60 degrees. There is no more forces in the y direction, so we set this equal to 0. And now we just solve this system of equations. So we can do here, for example, FAC equals to FBC sine 60 over sine 40. So this is equal to sine 60 divided by sine 40. 1.3473 FBC. So we can put this value into the first equation, and we have then 500 newtons minus FAC, which is 1.3473 1.3473 FBC cosine 40 minus FBC cosine 60 equals to 0. So we solve for FBC. FBC will be equal to negative, negative, so those positive 500 divided by 1.3473 cosine 40 plus cosine 60, 326.35 newtons. And then FAC from here equals to 1.3473 FBC, which is 326.35 newtons equals to 1.3473, 439.69 newtons. So we have ABC, FAC equals 440 newtons, FBC equals 326 newtons. And that will be it. All right, let's take a look at this control. This aircraft connection is acted upon these four forces, the forces P and Q, P 500 pounds, Q 650 pounds, and we are supposed to find the forces in the rods. So as we said, first we do a free body diagram, which in these cases is just a dot. And then we replace the forces that we know with this value and direction, and the unknowns with a good name, but they already have the names there, FA and FB. All right, in this case, it would be convenient if we set up the axis, the X and Y axis. Let's put the X and Y axis in such a way that the Y axis, the X axis coincides with the one of the unknowns here. Let's say this is the X axis here, X, and the Y axis perpendicular to that one So let's do it here. This would be the y-axis. And this will be the x-axis. X, y. In this way, when we do summation of forces in the y direction, the force A doesn't have component in the y direction, so the only unknown in that equation will be FB. So we have an equation we want to know that we can solve directly. That's the advantage of doing that change of axis like that. So now let's draw the other forces. So we have Q here. We have P here going down. P is 500. P is equal to 500. Q is equals to 650 pounds. And then we draw the other two forces. Let's do this. FB here. FB. and FA here. FA here. And now we have to draw the angles, the geometry. We have here 40 degrees. We have here 50 degrees. And we proceed to set up the equations of equilibrium. So we have to decompose the forces in the rectangular components. So we have here the components of FB. So we have here the force FBX and the force FBY. This will be BY. Then we do the components of P. We have here PY. And we have here PX. All right, so let's set up the equations. Summation of forces in the y direction will be better to start with the y direction because that equation will have only one unknown. In the y direction, we have the FBY force and the PY force. So FBY isn't going in the positive direction of y, so we can put that left. Like FBY, which is FB sine of 50 degrees. This is FBY. Minus PY, which is 500 sine of 40 degrees. And that summation, this is PY, has to be equal to 0. From here we can solve directly. FB equals to 500 sine 40 divided by sine 50. 500 sine 40 divided by sine 50 equals 419.55. Okay. And now we set up the second equation. Summation of forces in the x direction equals to 0. So x positive will be here. So we say Q, 650 pounds, plus PX, that will be 500 cosine 40 degrees, minus FA, plus FBX. FBX, if B is already 419.55, but to get the x component, we have to multiply by cosine of 50 degrees. And this equation has to be equal to 0. So from here we get FA equals to 650 plus 500 cosine 40 plus 419.55 cosine 50 equals to 3 pounds. So there we have the answers here. So there we have our solution. So A equals 330 pounds, and B equals 420 pounds. All right. Okay, let's take a look at this new example here. A sailor is being rescued using a boatswain's chair that is suspended from a pulley that can roll freely on the support cable ACB and is pulled at a constant speed by cable CD. So it's in equilibrium, constant speed, no acceleration. Knowing that alpha 30 degrees, beta 10 degrees, and that the combined weight of the boatswain's chair and the sailor is 900 newtons, we have to find the tension in the cable ACB and the traction cable CD. All right. So we're going to make a free body diagram of this element here. Will be a point. And then we're going to draw all the forces in this case. We have one force, the sailor going down. We know that one is the weight of the sailor plus the chair. That weight is 900 newtons. And then we have beta 10 degrees, so we have another force here at 10 degrees. Let's put this x-axis here. Put the axis here a little better here. The x-axis. So we can measure the angles with respect to that. So this will be the x-axis. So we have an angle of beta 10 degrees. Force. This is the cable ACD. So this cable has a tension on this direction and a tension on the other direction. Is a pulley. So we know that the tension in both sides of the pulley is the same. So we can call it T on both sides. This is going to be T and this is going to be 10 degrees. Now alpha is 30 degrees. So we have another force here at 30 degrees. This will be T. So this is also T. Same magnitude because this is a pulley. And then let's put it on this side, T. And then we have the force of the cable DC that goes parallel to this one here. The cable that is pulling the guy. This force is the force CD. Let's call it tension CD. This angle 30 degrees. So I have everything we need. The forces, the known forces with the direction and the value of the force well indicated there, and the unknowns with a convenient name. So now we have to set up summation of forces in the X and Y direction. Okay. So there is nothing we can do here to avoid. Oh, we could do. Yes, we could put the X-axis along the line AC. Let's put it here, another axis here to make our life easier. We could put the axis actually here. This is the X-axis. This is the X-axis, so not this one. And then the Y-axis will be here. If we do that, we eliminate the tension CD as an unknown in a summation of forces in the y direction. Let's take a look. Summation of forces in the y direction equals to 0. We have to get the components of this force. This will be dy, and this will be dx. So we have to find the angles with respect to this angle here is 30 degrees. So the whole angle of the tension here with respect to this axis will be 40 degrees. And what else do we need? We need the angle that the weight makes with respect either to the x or the y. So the rotation that we made here was 30 degrees. So that's the angle that we rotate here, 30 degrees. That was the rotation that we did to the axis. That was originally going through the direction of the weight. So now this moved 30 degrees in that direction. 30 degrees in that direction. All right. So our equation of forces in the y direction equals to 0 is going to look like this. dy, which is t sine 40, minus the weight cosine 30 has to be equal to 0. So from here we can find very easily that the tension is equal to 900 cosine 30 divided to sine 40. So this tension is equal to 900 cosine 30 divided by sine 40. So this tension is equal to 1257 newtons. Summation of forces in the x direction equals to 0. Oh, there is one component here of the weight in the x direction. I didn't draw it here, but well, doesn't really matter. We already used the y component here in the other equation without mentioning. So this is the wx, we can call it. So summation of forces in the x direction will be tx, that will be 1257 cosine 40 plus the weight x, that will be 900 sine 30 minus t, which is 12.57 minus TCD equals to 0. So from here we can solve for TCD, which is basically all this summation here on the left. That will be then equals 166.312.313. So then we have our solution here. The tension in the cable that they call ACB. The tension in the cable ACB equals 12 newtons, and the tension in the cable CD equals 166.3 newtons. All right. Okay, let's do one final example here. Let's see this one here. Determine the mass of each of the two cylinders if they cause a sag of 50 centimeters, 0.5 meters, when suspended from the rings at A and B. Note that the sag is equal to 0 when the cylinders are removed. All right, so here with the information that they are giving us, we can find the force on the spring because the geometry can give us the elongation of the spring. The original length of the spring, let's call the original length is L0 and the final length L. L0 comes from the square root of 1.5 square plus 2 square. That's the original length of the spring. There is a square root of 1.5 square plus 4. This is going to be 2.5 meters. 2.5 meters. And then if they say that the sag, when you apply the weight of the cylinders, the sag S is 0.5, then we will have here 0.5. So the total length, vertical length here is 2 meters. So the final length is equal to the square root of 2 square plus 2 square, the square root of 8, the square root of 8, 2.8284 meters. So the elongation of the spring is L minus L0. The length after is elongated minus the original length equals to, subtract these two values here. This minus 2.5. So it will be 0.3284 meters. So this is the elongation of the spring. So we go to the equation of the spring, which is F equals Kx. So the force on the spring will be 100 newtons meters times 0.32843 meters. So the force on the spring is 32.84 newtons. Now we can set up the equilibrium equations for ring A or ring B. They're symmetrical. So let's do ring A. So we're going to have the weight here, W, some force here that we don't know, we can call it the AD, and the spring force going here, which is 32.84 newtons. And since the horizontal distance here is 2 meters, and the vertical distance is also 2 meters, this angle is 45 degrees. 45 degrees. So we can set up a summation of forces in the y direction, where this is the x direction, and this is the y direction. Summation of forces in the y direction should be equal to 0 for equilibrium. So we have the component of the tension of the spring, 32.84 multiplied by sine of 45 minus the weight of the cylinder equals to 0. So from here we got that the weight of the cylinder has to be 32 sine of 45 degrees. So it's gonna be 23.223 newtons. And from here we can get the mass from weight equals mass times gravity. From mass equals to 23.223 newtons divided by 9.81 meters per second squared. So from here, divided by 9.81 equals 2.3673 kilograms. So our answer will be the mass of the cylinder. Don't escape, please don't escape. The mass of the cylinder is 2.37 kilograms. All right. So that would be a few examples. I recommend you guys to take a look at the examples on the book. I took examples that are not the examples on the book, so you have more examples to take a look, so you can see the total derivation on those. Example 3.1 and page 90, and examples 3.2, 3.3, and 3.4, starting on page 93 of your textbook. Okay, see you next time. Bye-bye.